Today's topic is conversion of finite automata into regular expression using Ardens theorem. We have three techniques to convert FA into regular expression. The first method is regular expression equation method, which is Keen's theorem, so which we have discussed in the last class, and in today's class we are going to discuss about Ardens theorem. First, let us see the Ardens theorem. We will have two regular equations P and Q over the input set sigma. If P does not contains epsilon, that's the most important point. If the P is not an epsilon, then the Ardens theorem is R is equal to Q plus RP. If it is in the form of R is equal to Q plus RP, we can imply it into R is equal to QP star. Let us see the proof. I am going to substitute the QP star instead of R in the first equation. So R is equal to Q plus RP. Instead of R, I am going to substitute QP star. So when I substitute QP star, you can see Q is common in both the equations. So Q is taken out. So Q into epsilon plus P star P. So by the minimization rule, number 9, that is epsilon plus R into R star can be reduced to R star. So it will be equal to QP star. Thus the Ardens theorem is proved. Now to apply Ardens theorem for converting a DFA to regular expression, it should have certain conditions. First condition, your finite automata should not contain epsilon. Second one, it should have only one initial state. It should not have more than one initial state. It should have one initial state. All the states must be a finite one. So it should have a finite number of sets. The last one is the regular expression must be expressed in terms of set of strings, which is accepted by the function or finite automata. That is, you will be expressing your states in terms of transition. So let us have an example. We are going to see 5 different examples for different classes. Let us see the first example. So first example, here we are going to have only one initial state and one final state. Let us see how it is done. Okay, so we will find the answer first. Okay, we are going to find the answer for the given finite automata. So condition 1, no epsilon, and condition 2 is only one initial state. Then only you can use the Ardens theorem. So here it is going to be Q1. Right. So what we are going to do here is we are going to represent all the states in terms of transition. Okay. We are going to do it in the terms of transition equations. So first step, we will start with from Q1. So Q1 has a self transition. So it is going to be Q1 of 0 plus it has a transition from Q3. So it is going to be Q3 with the input 0. Let us name it as equation number 1. Then now second transition is Q2. You can see you have from Q1 of 1, then you have a self transition for Q2 itself with 1, and you have a transition from Q3 with for the input 1. So we will be naming it as Q3 here. Next one is Q3, so which is going to be Q2 of 0. So we will name this as equation. Now to find the regular equation, so how do you find the regular equation? So the regular equation will be found only for the final state. So here the final state is Q1. So you have to find the equation for Q1 here. So let us start. First we will start substituting. We will find out what is the answer for Q2. Then we will substitute in Q3 and then you will go for Q1. So either way you can solve. The only thing is you have to solve here is using for this equation you have to solve this equation. So now let us see how it's done. So first, let me substitute 3 in 2. So what happens is, so what is the third equation is? Second equation is Q2. So Q2 is equal to Q1 of 1 plus Q2 of 1 plus, instead of Q3 you are going to substitute Q2 of 0 into 1. Now we will minimize this equation. So Q1 of 1 plus Q2 of 1 plus 0, 1. Okay. Now you can take this is Q, this is R, and this is P. So the equation is R is equal to Q plus P. So when you minimize this, you will get Q1 dot 1 with 1 plus 0 1 star. Why is it so? Because the Ardens theorem is R is equal to Q plus RP, means we can formalize into R is equal to QP star. So with that equation, so we have minimized into this equation. Let us name this equation as number 4. Now what you are going to do is, we know the value of Q2. Now first thing, we will substitute Q2, that is we will try to solve this. Q2 has to be brought in the first equation. We have Q3 here. So what we will do is, we will substitute equation number 3 in 1. So what happens? Q1 is equal to Q1 of 0 plus, instead of Q3 we are going to substitute Q2 0. So we will have Q2 0 into 0. Now what we are going to do here is, we are going to substitute the Q2 value, fourth equation, in this equation. So what you will do is, we will write it over here, substitute 4. So what happens is, it will become Q1 of 0 plus, so instead of Q2 we are going to substitute Q1. So Q1 into 1 plus 0 1 star, then finally this 0 will come over here. So you will have 0 here. So will be 0 0. Then you will have epsilon. I left epsilon here, so we will have epsilon also. Now we will try to minimize this. So you can see Q1 and Q1 is common in this term. So we will take Q1 out. So when Q1 is out, it is going to be 0 plus 1 double 0. I brought the 0 front, and then you will have 1 plus 0 1 star plus epsilon. Now this is again, you can see this is also, you can bring it to ordinal form, like this is Q, okay, and this is R, and this is P. So when you reduce it, you will have epsilon into the P term is 0 plus 1 0 0, 1 plus 0 1 star into whole star, using Ardens theorem. So therefore your final regular expression is equal to 0 plus 1 0 0, 1 plus 0 1 whole star of star is your final regular equation for the given FA, using Ardens theorem. Let us have another example. In this example, we are going to have a finite automata with 2 final state and 1 initial state. Again, so we have to check the condition whether the finite automata has epsilon. So this finite automata does not have epsilon. We have only 1 initial state, so that is Q1. So here the final state, we have 2 states, so which is Q1 and Q2. So your regular expression, the final regular expression will be Q1 plus Q2. So first step 1, so what I have to do, I have to form the states with terms of transition, equate the states in terms of transition. So we'll start with Q1. So Q1 is equal to, it has a self transition, so Q1 of 0 plus epsilon. So have it as equation number 1. So second one is, we'll take state 2. Again, state 2 has 2 transition. One is from Q1 with input of 1 plus Q2 with input of 1, which is a self transition. So we'll name this equation as Q into 2. Then we'll have third state, which is Q3. Again, it has transition from Q2, so which is going to be 0 plus, and a self transition with Q3 for both the inputs 0 or 1. So we will write it as 0 plus 1 here. So we will have it as third equation. Now what I have to do here is I have to find the equation for Q1 and Q2. So in the Q1 and Q2 you can see this equation does not have any term called Q3. So I am not going to use Q3 here. Only with Q1 and Q2 I am going to resolve it. So let us take the first equation. So Q1, which is equal to Q1 0 plus epsilon. So this is R, this is R, P, and I can have Q as epsilon. So what you can have is you can have QP star by the Ardens theorem. So you will be having epsilon into 0 star, epsilon into 0 star. So this is your equation number 4. Now what you are going to do here is I am going to substitute the value of 4 in equation number 2. So Q2 is equal to Q1 1 plus Q2 1. So now when you are substituting the value for Q1 here, it will be 0 star into 1 plus Q2 of 1. Again you can see this term is Q, this is R, and you can have 1 as P. So by applying Ardens theorem, so you can write it in the terms of QP star. So it will be 0 star 1 into 1 star. So this is your equation number 5. So now I have found the equation for Q1 and Q2, which are final state. So your final regular expression is nothing but Q1 plus Q2 equation. So your R is going to be Q1 plus Q2. So what is Q1? Q1 is nothing but 0 star, epsilon will not be there. And what is Q2 is you have 0 star 1 1 star. Okay, so your final expression we can simplify. If you are able to simplify, you can simplify. So I will take a 0 star outside. You will have epsilon plus 1 1 star by applying minimization rule. Okay, so if you apply the rule, epsilon plus R into R star can be represented as R star, that is epsilon plus R into R star is equal to R star. So if that, with that case you can write it is star 1 star. So this is your final expression for the given finite automata. So the next example we will have a little bit complex diagram. So this is the third example, how to convert a finite automata into regular expression using Ardens theorem. Okay, we will start our finding the answer. So step 1, there is no epsilon, condition checking, then Q1 is your starting state. So step 2, we are going to express all the states in terms of transition. So we will start from Q1. Q1 does not have any transition, only it is a starting state. So you will have epsilon alone. So it is going to be expressed as 1. So next one is Q2. You can see the transition is from Q1 and Q3. So you will write Q1 of 0 plus Q3 of 0. So you will have it as an equation number 2. Similarly, Q3, it has a transition from Q1, Q2 and Q3 with for the input 1. So you will write it as Q1 of 1, Q2 of 1 and Q3 of 1. So we will term this term as 4. Then final expression, the Q4 for the state. So it has a transition from Q2 for input 0 and it has a self transition. So we will write it as 0 plus 1 Q4. Now this is equation number 4. Now in this our final state is Q3. So our regular expression R will be equal to the equation of Q3. So we will start with the summation. So we will try to sum it. We are going to find Q3 here. So Q3 has Q1, Q2 and Q3. So I have to find the value for Q1 and Q2. First, let me substitute the second equation in the third equation. So I will substitute second equation in third equation. So let me write the third equation first for our understanding. So Q3 is equal to Q1 of 1 plus Q2 of 1 plus Q3 of 1. So here instead of Q2, I am going to substitute the second equation. So first I will write Q1 of 1 plus the second equation is Q1 of 0 plus Q3 of 0 into 1 plus Q3 of 1. So now we will formulate this equation. We will simplify. First Q1 of 1 plus Q1 of 10 plus Q3 of 10 plus Q3 of 1. So we will take the common terms outside. So we will have Q1 1 plus 10 plus Q3 10 plus 1. Now in this equation we will substitute Q1 value. We will substitute Q1 value. So when you substitute Q1 value here, it becomes epsilon into 1 plus 10 plus Q3 of 10 plus 1. So this is Q3. Okay. So now you can see this is R. This entire term is Q. This is R and this is P in the form of Ardens theorem. So I can write this term as QP star. So you will write it as first Q term 1 plus 10 and P star is 10 plus 1 star. So this is your final equation. So R into R star can be again reduced to R star. So your final expression is 1 plus 10 the star. So this is your final expression for the given finite automata. Okay, up to this we have seen two types of problem. Now this one is your initial state itself is a final state. Let us see how the regular expression is created for this one. Okay, we will find the answer. So step 1, check the conditions. So no epsilon. Here Q1 is your initial state as well as your final state. So it satisfies the condition for the Ardens theorem. So second step, you have to equate all the states in terms of transition. So we will start our transition. First we will start with Q1. So Q1 has a transition from Q2 for input B and it has a transition from Q3 for input A and it is the initial state. So you will have epsilon. We will term this term as 1. Next one is Q2. So Q2 has only one transition. It is from Q1 for input A. So now this is equation number 2. And now for Q3, you can see it is having a transition from Q1 also for the input B and we will translate it as name it as 3. And last state is Q4. So it is going to be Q2 of A. It's transition from Q2 and you have a transition from Q3. Then you have a self transition for both A and B. So you will write it as A plus B of Q3. Sorry, it's Q4. Okay, so you will name this equation into 4. Step 3, what is your regular expression? So your regular expression R is going to be Q1. Okay, so you can see Q1 is having only Q2 and Q3. So we will be using only the first 3 expressions. We will be not using the fourth expression. So first step you will do is substitute 2 and 3 in the equation number 1. Since it is a simple equations, we can do that. So let me write the equation 1 first. So Q1 is equal to Q2 into B plus Q3 into A plus epsilon. Now instead of Q2, I am going to substitute Q1 A dot B plus, then instead of Q3, I am going to substitute what the value. So Q1 of into B into A plus epsilon. So now we will take the common term out. So we'll take Q1 out. So you will have AB plus BA plus epsilon. Now this is in the term of Ardens theorem. So this is R, this is P, and this is Q. So I can write it as Q P star. So which is epsilon into AB plus BA star. So epsilon into any regular expression is a regular expression. So your final regular expression is AB plus BA the whole star is your regular expression. Let us see the last example for conversion of FA into RE using Ardens theorem. It's a little bit complex. So we'll find the answer. So your first step, it's no epsilon. Second one, your initial state here is Q1 and your final state here is Q4. So your regular expression R is purely dependent on the equation Q4. So step 2, all the state must be expressed in terms of transition. So we'll start from Q1. So Q1 is equal to Q1 of a self transition, plus it has a transition from Q3, it is Q3 of A. Then from Q4, you have a transition for A. Then it's an initial state, so you will have epsilon. We'll name it as equation number 1. Now we'll go for the state 2. You have a transition from Q1 for B, a self transition with B, and you have a transition from Q4 with B. So we'll name this term as second equation. So next one is Q3. So Q3 has only one transition from Q2 with input A. So we'll name this equation as 3. So we'll name this equation as 3. And the final state is Q4. So which is having only transition from Q3 for the input B. So we'll have this equation as 4. Now you can see all the equations are interlinked. So I need to find Q4. So Q4 is dependent on Q3. Q3 is dependent on Q2. Q2 is dependent on all the expressions 1, 2, and 4. And if you take 1, it is 1, 3, and 4. So first what you'll do is we'll try to find what is the equation for Q4. So what I'm going to do here is I'm going to substitute 3 in 4. Okay. So Q4 is equal to Q3 of B. So instead of Q3, I'm going to write Q2AB. Let us name this equation as number 5. So Q4 needs Q2. Okay. So now you'll minimize Q2. So what I'm going to do here is I'm going to substitute the value of Q4 in the equation number 2, because Q4 is there in Q2. So we'll substitute the 5 in second equation. So you will see Q2 is equal to Q1B plus Q2B plus, instead of Q4, I'm going to substitute fifth expression. So I'll put it in a bracket for our understanding, AB into B. So we'll minimize this equation. So Q1 of B plus here Q2 is the same way. So you will take Q2 out. So we'll have B plus A, B, B. Now this is of ordinal form. So this is Q, this is R, and this is P. So when you write it, you will write it as Q1 into B, B plus A, B, B star. So we'll name this equation as 6, and this is done by Ardens theorem. So the next one we are going to minimize is Q1. You can see Q1 has Q3 and Q4. So Q4 we found the value over here, and you have a Q3 value over here. So we will substitute the third equation and fifth equation in the equation number 1. So first I'll write substitute third and fifth expression in equation number 1. So let me write the equation number 1. So Q1 is equal to Q1 of A plus Q3 of A plus Q4 of A plus epsilon. So now we are going to substitute Q3. So I'm going to substitute for Q3. So Q3 is going to be Q2 of A into A plus, and Q4 is, again it's in terms of Q2, it is Q2 AB into A plus epsilon. So now this Q2 is common in these two terms, we will bring it out. So Q1 of A plus Q2 into AA plus ABA. This is plus epsilon. Now instead of Q2, I can substitute the sixth expression here. So what is your sixth expression? You can see here Q2 is equal to Q1 of B. Okay, so we'll substitute the sixth expression in here. So when you substitute, it will become Q1 of A plus Q1 of B into B plus ABB star into A plus ABA, okay, plus epsilon. Now Q1 is common in these two terms. We'll bring the common term outside. So Q1 A plus B, B plus ABB star AA plus ABA. We'll put a bracket and here. Now this is in the term of Ardens theorem. So you can see this is the dot where I am standing is R, the remaining terms are P, and the last epsilon is Q. So when you write it by applying Ardens theorem, it is epsilon into A plus B, B plus ABB star A plus ABA whole star. Let me have this as an equation number 7. Now you have to find the value for Q2. We'll see what is Q2 here. Okay, so in the seventh experiment, in the 7, you are going to substitute the value of, we have found the value for Q1 here. So this Q1 value will be substituted in this equation, in the sixth equation. So because sixth equation Q2 is having Q1, so I need to find the value of this one. Okay, so what I will do is I will substitute the seventh equation in sixth equation. So this is Q1. So what is your sixth equation? Your sixth equation is Q2 is equal to Q1 into B plus B plus ABB. Now instead of Q1, I am going to write this. So I will write entire term. So A plus B, B plus ABB star and AA plus ABA the whole star into B, B plus ABB. Now we will term this term as 8th term. So why do I have to find Q2 here? So as you can see in previous term, Q4 is expressed in terms of Q2. So I need this Q2 value. So I found the Q2 value in 8th expression. So now what I do is I am going to substitute the Q2 value in 5th expression. So what I do here is I am going to substitute 8th expression in the 5th expression. So that means your Q4 is equal to Q1, it is Q2 AB. So instead of Q2, I will substitute this entire value. So what happens is A plus B, B plus ABB star, okay, I don't want this one, okay, AA plus ABA whole star into B, B plus ABB, then finally you will have one AB. So this is your final expression. If you are able to reduce it, you reduce it. Otherwise, you can just keep it as it is. Now this is the regular expression for the given finite automata. So that's all for converting an FA into regular expression using Ardens theorem. I hope I have given enough examples to explain how FA is converted into regular expression using Ardens theorem. Thank you.